All right, hello everyone. Welcome to another month of the HEIR meeting. So we had a little bit longer since last meeting due to the holidays, but we had 34 PRs merged. The theme is we've been improving the machine learning pipeline for CKKS quite a bit. And we've also been adding a bunch of new kernels and improvements to the implementation of various like baby step, giant step type things. Okay, let me go through it. We had some improvements to the use of the arithmetic DAG. In particular, we added a fuzz testing framework so that we can unit test all of our kernels without having to run like end-to-end MLIR tests, which is quite nice, I think. So most of the kernels should be fuzz tested now. And we're finding it helpful to find new bugs as we are writing new kernels. We have been removing the tensor dialect. I think we're going back and forth on tensor and memref from CJGI, but I think Wouter can talk a little bit more about that maybe in the discussion section. But yeah, so there's some work going on the TFHE Rust backend vis-a-vis the FPGA stuff. So we have our layout optimization got a new cost model for the kernels that looks at the arithmetic DAG of the kernel and evaluates, I think it evaluates the number of rotations and or the multiplicative depth. There's still, I think, a lot of work to do there, but this is just like a first pass. We also had some improvements to the shift network implementation. Basically, a bunch of our kernels were we were experiencing. We wanted support in our pipeline for like tensor operations like insert slice and extract slice, and some of those would result in extracting a slice from like a packed tensor, and then it would have to replicate it to achieve the right output packing necessary. And that is like not too expensive, but the problem was that the shift network was having lots of conflicts in the way that the graph algorithm works. So there's all these conflicts in when it tries to replicate a vector in this way. And so we did some improvements to like deduplicate some of those conflicts in a way that seemed to make sense. But yeah, I think there's an issue on this topic for like solving this more robustly. We had improvements to the convolution kernel. So now we can run end-to-end 2D convolution using the Orion kernel and we get the correct answer. So the next step is to like actually run a whole end-to-end CNN using this kernel. And then we added kernels for matrix multiplication, both ciphertext and batch ciphertext matrix multiplication. So these were both from the bicyclic and tricyclic layout and kernels from those two papers. I think what's still missing here, I think the bicyclic layout is in the whole pipeline. The tricyclic one is not yet integrated in the whole pipeline. And the other thing that's missing from these is we don't do yet any special padding of the input data matrices in order to meet the divisibility conditions on the dimensions that's required for those kernels. So there's still some work to do if you want to actually use these kernels for like an end-to-end model. But yeah, I think once we get CNNs working, which only need plain text ciphertext matrix multiplication, then we'll focus on some more ambitious stuff that needs these, and we'll finish implementing that. Then there was in doing this, we noticed that our like baby step, giant step reductions were not optimal. Like the choice of the split between the baby steps and the giant step was not optimal. So Lawrence Lim helped us with optimizing that. We had a bunch of tensor ops and canonicalizations that needed to go through the pipeline to make our CNN cleaner. We have some more doc tests on different passes. So this is more sort of like incidental work. plain text linear algebra ops can now be hoisted out of a secret generic. I don't remember why they weren't, but I think it was some incidental thing. Okay, so there was one of our issues was that we were doing parameter selection for these like big, fully unrolled CNN things, and these insert management passes just like fell over because they were doing a quadratic data flow analysis. So it would change one op, rerun the data flow analysis for the whole IR, change one op, rerun the data flow analysis for the whole IR. So I looked into that, and it was not necessary to do that because the data flow analysis was kind of only looking backwards, I think. Or sorry, it was only looking, yeah, I forget. It was going forward, but only looking forward. So when it updated an op, it didn't need to look backwards again. There was something like that where it was like, oh, it's not actually using most of the data that it's updating. And in the some of the places that it did, I was able to just like mutate the analysis in place. So I did some like fancy thing to sort of like bypass some of the necessary or some of the recomputations of that data flow analysis. But so now it's much faster. I think we're still looking into, we started to, like, I think because of this and some other issues, we're starting to look into like different ways to do parameter selection. But yeah, I think that's TBD. We also have a sigmoid activation. I think the Linnet MNIST, the Linnet CNN that we have down here, that's like our case study that we're working on this month, uses a sigmoid activation. So this adds support for that activation. And then, yeah, this one, I don't remember why we did this, but we had our parameter selection was using some way to select primes, and that was different from the way OpenFHE was selecting primes, and we decided it would just be cleaner to mirror exactly what OpenFHE is doing and how it selects its primes. I think this is like a step towards doing high precision scale management, which is something I have in the work in progress section. Okay, in one of the evaluations I'm working on is against Orion, and Orion uses Latigo, and Latigo has a very particular way of doing polynomial evaluation with Patterson-Stockmeyer, which is very close to what we do, but there are a couple of small differences, and in analyzing the performance differences between HEIR and Latigo, I found what these differences were and realized that we were just doing it inefficiently, or a little bit less efficiently, and so I updated us to now we produce the exact same circuit as Latigo does in this case. And I think there's still some more we can do with like improving the scale management in these circuits, but that's for later. In working on the Orion comparison, for both Orion and for DeCapo, what we're doing is we are taking their IR and we're converting it to CKKS IR in HEIR and then lowering to HEIR's backends. And that is supposed to remove some of the differences between these different compilers by only actually testing, the compiler backend, or the way it invokes the chosen backend might be different between those two. So we're saying, okay, we're just going to lower to HEIR and have HEIR handle the backend, and then that will be more of an apples to apples comparison. In doing that, we need to generate CKKS dialect LWE types from these ops, from these external IRs, and it's just annoying to build all these types with all of these different parameters. So I added some type inference hooks on these so that you will be able to, if you're doing a mod reduce op, you don't need to construct the result type separately from the input type. It will just infer what the proper result type is by dropping the last limb. So this is a bit nicer. And then in all of these, we're also testing timing with OpenFHE, and we noticed that our OpenFHE backend was slower than expected. So some of the things I did was I added a timing table. So we have this OpenFHE interpreter. It was very slow because it had a bunch of random C++ overhead that I have fixed. But it was also, because it was slow, we didn't know, okay, is OpenFHE ops being slow? So I added this timing table to the interpreter. So if you run it with this flag enabled, then it will spit out a table of the OpenFHE ops and how long they take, like in aggregate and on average. And then I added a separate OpenFHE benchmark binary that takes the OpenFHE upstream benchmarks and ports them to our Bazel build to make sure it's not our Bazel configuration that is causing the thing to be slow. And that confirmed that that was not the problem. And at the end of all of this, I figured out that what was the problem was that the default scale management choices that are being made by OpenFHE in our use of it is different from what scale management choices FHE uses in its benchmark. So its benchmark picks a very particular scale management that is faster. And then in HEIR, we use whatever it lets as the default. And it's 2 to 10 times slower depending on your ring dimension. And so by setting the ring dimension and the scaling method exactly to the same as what OpenFHE is doing in their benchmark, I confirmed it's not our Bazel build that's the problem. It's just how we are, what settings we're using for OpenFHE. So, okay, fine. Yes, okay, this was another little bug in the interpreter that was fixed. And then, okay, now this is a more heartwarming one. Yeah, so Rotom now has the first step of lowering to HEIR. So we have the Rotom discovered packing for a chained matrix multiplication. We just have the IR exported to HEIR and then checked in as a unit test and tested to make sure that it runs correctly. Okay, whew. For in-progress PRs, I wanted, in my attempt to get Orion to lower to CKKS, so Orion does not actually implement its Chebyshev evaluation, nor does it implement its baby step, giant step for matrix vector multiplication. It just uses a function from Latigo. And so my first thought was like, oh, okay, I'll just use our existing kernels for these things and lower them in HEIR. And that worked, but it required us to insert additional bootstrapping ops because of our lack of proper scale management, or the fact that our scale management doesn't match what Latigo does. Part of the reason that we can't do what Latigo does is because we just have like log bits number, or like number of bits in our scale management. So we don't actually represent the individual primes when we're analyzing scale. And so what this PR is attempted to do is to start support for having high precision scale management in HEIR, where we actually track the exact scale. It shouldn't be hard to do this because they're all just AP ints, but there's like a lot of changes in the scale management section of the pipeline. And I had an LLM try and do a first pass, and then I haven't come back to it to actually see how well it did and what is left to be done. So, but anyway, so this is something that I want to do. I don't think it's blocking anything for us at the moment, so it might not get done for another month or so, but that's there. There's a PR for broken tests in the TFHE Boolean pipeline. I don't know what this is. I'm assuming Wouter worked on it, but okay, anyway. There was, oh yeah, this is another work in progress PR where in OpenFHE, we have this eval fast rotation API that lets you pre-compute the first entity of the rotations and then share it among later rotations. Latigo has the same thing, but we don't use it yet. So I was going to port the same kind of pass to Latigo. And then I don't know if it's possible to share the logic between these two things because the APIs are very different between Latigo and OpenFHE, even though it's like effectively the same thing. But Latigo, you don't pre-compute something and pass it on. You just give all the rotations that you want in one go, and it kind of does the pre-computation inside the function and all of the rotations at the same. Yeah. So anyway, it does things differently enough that maybe we can share the analysis, but not the actual code changes. Yeah, okay, so this PR, this is done in review, and it's converting Orion to Latigo. So this one is now lower, instead of using our kernels for Chebyshev and matrix vector multiplication, it is just lowering those Orion ops directly to the corresponding Latigo API calls, which required me to add support in the Latigo dialect for Chebyshev and linear transform, which is like not the most trivial API to have in Latigo, but okay, it's fine. I think it works. And then, okay, so we're working on this new Linnet CNN as like a test case. And the biggest performance issue that we found was that the Orion kernel produces a linear transform operation that has a lot of zeros in it. And so we weren't looking for the zeros and skipping them, right? Because a plain text multiplication by 0 is just doing nothing. So you were actually computing all of those, and it was just a wasted computation. And it was something like 50 to 75% of the diagonals were 0. So we had like,
I think Jeremy froze.
Is it just me or no? Okay, yeah.
It's okay. I was late to this meeting because I have Spectrum Internet and it's not the best internet service provider in the US. And like, I just couldn't have internet for 10 minutes.
I had some connection issues earlier, so I thought it was me at first, but I think, yeah. Well, do you just want to rock on with
I can keep
intro
going.
response?
Yeah, I mean, I was the one who wrote this PR. So yeah, we were, this was like a product of that Lynette example. And it slashed the runtime, I think, like 20 seconds off of it, which was really nice. So that has that example in it. And I think Jeremy.
Are they both frozen now?
I think we just. Oh. Oh, God. What is up with the. Okay, I think we also lost the screen sharing here from Jeremy now. Great. Do we have any of them back? Technical difficulties. I think we kind of maybe still have Astra, just at a very low bit rate. Yeah, I tried screen share, but unfortunately I'm on my iPad. I didn't bring my laptop with me to my family's place, so I don't think I can actually screen share. Do we have Jeremy? Welcome back. I think you muted, Jeremy.
my internet just completely crapped out for no discernible reason.
Yeah, and then Astra was about to take over, and then her internet died. So.
Oh no! Really? Wow! And we're at different parts of the country. Okay. Woo! Okay, where were we? Okay, so we're working on this Lynette CNN. The diagonals were the biggest part. We were able to remove them, and then I think the Lynette example is now running at something like 30 seconds per inference, which is like not super great yet, but there's still more to do. So, and I think that's like 2 convolutional layers and 2 fully connected layers, something like that. So it's still relatively small, but okay. And then what is this? So I think the other thing, I still have a conversion from Orion to CKKS that actually does use our kernels, and as a consequence of our messed up scaling, inserts additional bootstrap operations. And so that will at least allow us to test what they're doing on OpenFHE. I don't know how useful it will actually be though. Okay, yeah, so this was the PR where I said there was a bunch of overhead in the interpreter when I was testing it on the Lynette example. It seems like I was able to eliminate all of the overhead. And then, yeah, there was another segfault issue that got fixed. And then this was now the other thing that I think Asa was working on with Lynette is using concrete bounds from the intermediate layers of the IR to choose the polynomial approximation domain interval. And so I think that we hope that by tightening that interval, we can get away with smaller crypto system parameters. So that might give some more performance. Yeah, sorry, I'm back as well. I heard, I don't know how that,
Yeah, it's curse of whoever drives this meeting.
yeah,
It's
okay.
contagious.
Yeah. Okay, so I just got through all of the stuff, all of the in progress PRs. Notable new issues. I think there's a bit of things that we can do for the kernels. One of the more interesting ones is to like the tricycle paper has this optimized ciphertext plaintext matrix multiplication, which would be pretty cool because I think most of the matrix multiplications in ML are actually ciphertext plaintext matrix multiplications and not ciphertext multiplications. I think transformers is the one exception, but this one is nice because the plaintext has no limits on the dimensions of that plaintext matrix, whereas the ciphertext ones have like it has to be like whatever. I think they all of the the entire matrix needs to fit inside of half of a ciphertext or something. So there's like a pretty strict limit here, but the plaintext one, they have a way of doing it without any limitation on how big the plaintext matrix is, which is pretty cool. And then there's still issues with the PyPI release. I'll talk about that in a little bit. There was this new FHE scheme, fully homomorphic encryption for matrix arithmetic. This was Gentry's new scheme, where they use like the homomorphic trace operation to do just like matrix multiplication, reducing matrix multiplication for ciphertexts to plaintext or clear text matrix multiplication on like the underlying RLWE samples, which is kind of cool. Yeah, okay. I don't know. I wanted to read this paper. I started reading it, and it might be nice to have like a new scheme if we, or there's no library implementation of this. So like maybe we could implement the crypto in the compiler and then get this and have this be like the first implementation. I don't know. Probably it won't be the first implementation because I think Gentry implemented it on top of NTL or something, right? But I don't think they published it. Anyway,
I've also been trying to wrap my head around that paper, and it seems like the memory penalty you pay for this because you think you need way larger keys. I think the keys blow up by like a factor n or even n squared or something horrible. So I think, yeah, I want to really do some like pen and paper like complexity analysis or like approximate-ish with like some wiggle factor, because I don't know, it sounds really cool, but I wonder if maybe it's trading off a lot of memory, which is usually bad, right, in like actual systems. I think as far as I know, nobody has like done any real compilations with like real computations with it, right? So it would be very interesting to see what this performs like for a real like large scale model, for example.
Yeah. Okay, then there was another issue where we noticed in some of our polynomial evaluations that the Chebyshev polynomial like reduced to a much simpler polynomial in the monomial basis, but we were creating a larger circuit than we needed to. So I thought one nice little feature would be to have a thing that checks to see, okay, if you convert to the monomial basis, is the polynomial going to be simpler than in the Chebyshev basis? And then maybe you can get a smaller circuit. I filed this issue, and then like hours later, a random person submitted an LLM generated implementation of this. So there is a starting PR, and I think maybe there's something to discuss about what should we do if we get random LLM submissions for with that seem like there's no human involved. But I ended up closing that PR. But if you want to steal their work and patch it and improve it, I think that's fair game because you can't steal from an LLM. Okay, so. Okay, so yeah, there was an issue with our CI where if you rename a pass and like move the files around, then you need like a cache invalidation of the GitHub action in order for this job not to break. So there's an issue that's tries to fix this, or the goal is to fix this so that it doesn't happen. Even though we don't rename passes very often, if you do rename a pass, you'll get this error. It's like it will still see the old table gen and then it will try and create a documentation file for that table gen, and it won't be able to find like your doc test or some associated files for this, and it will fail. Okay, this one, I think I closed this issue. This was when I was investigating the OpenFHE timing, and I thought it was the Bazel build. Okay, so in the DeCapo paper, there is a technique that they use. I mean, the main thing they do is they have loops, and they do bootstrap placement in the presence of rolled loops without unrolling them. And one of the things that they do is they say, oh, well, if your loop is not that big, then you might not need to bootstrap all the way up to the top level. And there's a facility in bootstrapping where you can, for less amount of computation, you can bootstrap to a lower level than as much as possible. And so they say, okay, if we only need whatever small number of levels, you bootstrap to a lower level, and then you keep doing your loop, and it might be faster. Or I think this also happens at the end of a program if you only have like 10 instructions left and you don't need a bootstrap all the way to the top. But no backend that we know of supports doing this. And the DeCapo people, they added like a custom implementation on top of HEIR in a private repo that we can't have access to implement this. And then in their public backends, I think they just cheat and they decrypt and re-encrypt. And then I think the other people we've talked to will bootstrap to the highest level and then just level reduce down to the level that you want, which is like more expensive. So, okay, so our timing is going to be a little bit off for DeCapo comparisons versus what's in their paper, but for a good reason. And so now we have, I think, an IR level op that says you can bootstrap to a lower level, but no implementation of it, or no proper implementation of it. Okay, and then yeah, there's all these issues about Wheels workflow. I tried to automate the PyPI publishing, and that's failing. Did someone have something to say? No.
I was just saying the like partial bootstrap, I think, also is used outside of DeCapo. For example, the Nexus paper, secure transformer, whatever inference made non-interactive one, and the follow-up papers, they also use this where I think for certain parts, like they basically bootstrap like 2 or 3 times inside one like block, one layer of transformer, and one of those is like a full one, and the other 2 are only to a partial level. So I think they obviously have a GPU backend, but they also, I think, allegedly have a CPU backend. So I wonder if that backend maybe has a code implementation that we can look at. Because I know they implemented the custom bootstrapping for their GPU backend, but I can also check if they maybe have a CPU version of that.
Cool, that'd be helpful. Okay, for OpenFloor, last meeting of 2025, we're not meeting on Christmas, and then the next meeting will be in January, I think end of January, so we'll be 2 months till the next meeting, and that should make sense because I assume most people won't be working over the holidays. Okay, so one of the things, okay, I can't release to Python, the Python package to PyPI, so it's quite old what's on PyPI. I was able to actually completely fix the macOS build for that deployment. So I can build for PyPI on macOS, but now the Linux build is broken. And I think what happened was when we updated OpenFHE some point in the last few months, they started using code that requires a newer libc ABI. And when So the way this thing works, CI Build Wheel is this platform for doing Python packaging, and they are very restrictive on how new of a libc version you can use. They don't have like more recent containers that allow even newer libc versions. So if the C++ code that you're compiling uses 2 new features, then it will just crap out and give up and say, oh, I can't actually build this wheel, or it can build the wheel, right? It can build everything just fine, but then there's this step of auditing the wheel to make sure it can run on all of these Linux versions. It's what's called mini Linux. That would be one Python package that can run on pretty much any Linux. And they say, okay, this fails, and so then it won't finish the build. So I don't really know of a good workaround for this. I have this this PR that I filed that has some of the debugging information in it, but you can see, if you look in there, you can see that it's only OpenFHE shared libs that is messed up. So I don't know quite what that means. I have to think about what to do. One option is to give up on this CI build wheel thing and try to do the Python builds manually on the platforms we care about and do the packaging manually. That's a bit of a rat's nest, just because Python packaging is complicated. I don't know exactly how to do that, but the other option is to try and get CI build wheel to just ignore the fact that it's an old lib. There's a newer, like just say like, okay, CI build wheel, allow me to use the newer libc and just like publish the Python package anyway. I don't care. I don't know how to get it to do that either. So yeah, so that's why we haven't published any Python stuff, but we still have the like GitHub releases of HEIR that are happening every month. But yeah, so if anyone knows any Python packaging experts who want to help with this, I would be welcome. Okay, right, and then benchmarking. Yeah, so this is sort of like an outline of the benchmarking work that we're doing. We have this Linnet inference model that we've been using just on our end as like a first convolutional neural network that's interesting. That is basically working, but we're trying to get some more testing of performance and get things to be faster. I was working on this Orion lowering to HEIR, which is working, but only through Latigo. We have the Da Capo, I think lowering to, I think Asra has this code, but it's not been pushed yet. So it's like basically done. This one was much easier because their IR looks a lot like our IR does already. And there's just that caveat around the CKKS level for bootstrapping. And I think the other caveat is that they don't actually have real data. Their compiler just puts in like zeros or garbage data for everything. Yeah, so well, more updates on that, and then Edward's work on Rotom. So yeah, so we have these three. I think these are going to be the three things that we compare. And so the next step for me is to actually get the specific models that will be going into each of these for testing. I think the problem is that, like, if you look at Orion and Da Capo, they both do a multi-layer perceptron, but the architecture of that multi-layer perceptron is not the same. They pick their own version of multi-layer perceptron and they put it through their compiler. So I need to figure out, okay, how can I get the same actual model to go through all three of these? I was thinking I would start with a multi-layer perceptron and then maybe something simple like a ResNet 10 instead of a ResNet 20. The reason I say ResNet 10 is because ResNet 20 makes Orion require more than 100 gigabytes of RAM, and I don't have the time to deal with configuring all that stuff. Question also says, Orion assumes all of the plaintext are passed in as function arguments. Yes, that's true. Orion pre-computes all of these diagonals, saves them to external files, and then you load them in. And I think I mean, I think we don't quite have that feature in there. We still, but we can manually do it by like taking our function signature and having the plain texts be passed in as function parameters. But we can also do it statically. I mean, we have some feature ongoing that we're working on where it's like you will allow the IR to decide what plain texts to pre-pack. And then you get like a different function that allows you to run the pre-packing as a separate step. But anyway, yeah, I think we might, I don't even know if we need to do that in January. I think January is going to be us crunching on the paper submission. But yeah, so basically, Edward, I'll be coming to you sometime early January with the models that I think we should run. And then hopefully this week or next week, I can get at least the Orion and Da Capo examples, like just some runtimes written down that like I can reproduce. Okay, and then those are the topics I have. I don't know if anyone open the floor, please. Who wants to talk about anything?
One really quick note about that
mention.
Orion thing. Then the Da Capo one does everything in line with their fake weights, so that they encode in line. So as long as we like, I mean, there's nothing we can do about that. I don't think we should like go through the effort of like splitting that out. But we'll have Da Capo doing encoding overhead.
I guess if we use the timing table, we can just like subtract the time it takes to do all of those plain text packings from, well, no, actually, no, that's not true. So hold on. Orion assumes that the diagonals are passed in as clear text. And because they don't implement any of these operations, and Latigo takes the diagonals as clear text, and Latigo internally packs them like at runtime. Yeah, so they're both packing at runtime.
Yeah. Also, Jeremy just mentioned the paper, and I want to point out that we do have the archive preprint of that. So if, let's say, hypothetically, you're citing github.com/Google/HEIR right now in your papers, please update it to the archive version so that we get, Google Scholar citation counts and things like that. I think, I know Rotem, I think, cites the GitHub link still, right? So please, we need citations.
Now, let me see what else. Yeah, I can't. I'm going to be down in Sunnyvale next week. I'll be giving a talk to Kornami, going to their headquarters to chat with them about compiler stuff. I can't think of anything else. Yeah, we're just focused a lot on getting these neural networks to compile.
I have something slightly off topic, but I found this very interesting and wonderful paper from 2023 about how to train low-depth polynomial activation functions for deep convolutional neural networks. And I think their main insight there is when you're creating these low-depth polynomials, you need to have some sort of bound on the input ranges for those polynomials. And then having these bounds guarantees that you don't have these accuracy degradations when you then convert that to FHE. And I think their evaluation shows that ResNet 18 takes 30 minutes to run, even though their polynomials are much, much simpler compared to the state-of-the-art polynomials used for high accuracy values. But I think the reasoning why that's the case is they don't focus on either packing or bootstrap placement. So I think if we take all the things together, we can get ResNet down to on the order of minutes, if not seconds.
Exciting. Because I know Orion claims they get ResNet 20 in 10 minutes, I think, for one inference, and they don't do any polynomial fine tuning. And you're saying they retrain?
Yes, they do retraining. And I think Orion's case, just do a comparison. They have one evaluation where they replace every single value with 18-degree polynomials. So that's a multiplication depth of 5. And I think for Orion, they're doing, I think it's the 15, 15, 27 composite polynomials. So that's the multiplication depth of 14. So the number of bootstraps that you say would probably be at least half. I think there is one follow-up work on this paper from a different group, but the paper isn't as exciting in my opinion.
I mean, there was one other paper.
Was it smart?
Yeah, smart. Yeah. That was by Jianming, who was our student researcher. So, and I remember I think they do post-training fine tuning or something.
Yes, they do.
I imagine that's not going to be better than doing it during training, right?
I don't think so, but also my ML knowledge here is not that in depth.
No, it's not. Retraining is always better.
Yeah, there's the
I also
smart
think
paths,
we should maybe be.
There's the self-learning activation functions as well. But self-learning activation functions only tested on MNIST, and they didn't try it on anything larger.
I think we need to be careful with the retraining stuff, because that's an easy thing to do for academic benchmark things where everything is open source, open data, open everything. But I think a lot of the cases where FAG is interesting, you probably want to have a model that you don't need to modify. So I think it's we need to be very careful, especially also if we report this in papers. There's a huge difference between running a model from Hugging Face and running some fine-tuned, retrained whatever version, right? So I think it's nice that you
Well-
can get these speed ups, but in some sense, I feel like it's more educational to look at the performance we get when we don't do it, right?
That may be the case, but I'll at least say at Google, I don't think we're going to be taking any off-the-shelf Google models. We're going to be
Right.
retraining
Yes.
them.
Yeah.
Yeah. So the performance is critical enough that I think if we don't do that, we're not going to. Yeah.
Yeah.
It's not going to be practical.
I think honestly,
yeah,
in
so
that
it's
case,
like-
you're probably better off training from scratch, right?
No, that's what I mean.
Um,
It's not. I don't think these are retraining. I think they're training
Yeah.
from scratch. They're just training from scratch with some FHE awareness.
Right. From scratch. Yeah. Yeah.
And I think honestly, what we're looking at is like also changing the architecture of the model. Like, do whatever it takes as long as you are, as long as you can run an FHE and you get good accuracy. Like, we don't care what the architecture is.
Isn't like MNIST solvable by like a KNN or something?
I'm sure MNIST is solvable with if
So we need to be
statements
careful that we don't
based.
solve to linear equations.
Yeah.
Anyway, cool. But no, these are really cool. I know there was also a paper called Pan or something that also looked at like optimizing polynomial approximations for neural networks or something. But I don't know. Yeah, something like that, I think.
I mean,
Yeah,
there was
I don't have a link
another
for that unfortunately right now,
paper. There was another paper called like CryptoFace or something that we saw recently. I'll post it in here. And this was one where they like completely modified the architecture to be more FHE friendly. But it was also very disappointing. Their runtime latency is like 1500 seconds or something, like 10 minutes. No, that's like 30 minutes. Yeah. So good that changing the architecture works, but 30 minutes is still quite bad. So I would love to dig into that and figure out like why it's actually still so slow.
Quick
nearly a decade-old
elaborate on
master
the
thesis
topic.
wants to also disagree on this being the first, because I think that like eigenvector-based face recognition for my master thesis, and it's like that's plenty fast, but I guess it's not good enough for like real like biometric security, right? Because it's, like the recall is pretty garbage for that, for example.
And we're planning to add CryptoFace to the benchmarking suite as one of the workloads. So when it gets it faster, it will be cool to see.
Oh, it looks like it's also built off of Auto FHE, where Auto FHE is like a system where they basically do some sort of search to see if they can replace the values with squares. Yeah, I think there's some insights where essentially like the earlier values in your layers have to be high accuracy, but then the later values can all be like replaced by square activation functions. And then that could lead into other insights where like maybe you do some sort of layer, like during retraining, some sort of layer-wise like figuring out what depth you need your polynomial approximations to be per layer.
All right. I'm out of topics. Anything else? Cool. All right. Well, then I will see you guys all in 2026. Have a good one.
Bye, guys.